Morning, good afternoon, or good evening, depending on where you are in the world, and welcome to today's Plastics Today webinar, Reconsidering Metal 3D Printing for Tooling, New Method Unveiled, sponsored by Mantle and broadcast by Informa. I'm Michael Krieger. I'll be your moderator today. We have just a few announcements before we begin. First of all, this webinar is designed to be interactive. The dock of widgets at the bottom of the screen will allow you to learn about today's speaker, download resources, share the webinar, and participate in the Q&A session that takes place at the end. The slides will advance automatically throughout the event, and toward the end of our webinar, we'll ask you to complete our survey found on the right-hand side of your screen. Please take a minute to fill this out before leaving us today, as your feedback provides us with valuable information on how to make future events better. Finally, if you're experiencing any technical problems, please click the Help widget found on the bottom of your screen, or type your issue into the Q&A area, and we'll be glad to offer one-on-one assistance. And now, on to our event, Reconsidering Metal 3D Printing for Tooling, New Method Unveiled. Joining us today is Paul DeLaura, Chief Commercial Officer of Mantle, who will be discussing today's topic. To learn more about Paul, just visit the bios page. Paul, thanks for joining us, and over to you.
Thanks, Michael, and thanks everybody for joining. It's a pleasure to be here today. So today's session is really intended for those of you in the plastics industry and the toolmaking industry who are interested in metal 3D printing. Maybe you have some experience in metal 3D printing, and you're interested in understanding how it can be applied to toolmaking and to plastics production. And we're also going to talk more about the technology from my company, Mantle, which is relatively new to the market and designed specifically for helping companies to speed up and reduce the costs associated with making tooling. So what we're going to cover today is first just a brief introduction to who we are at Mantle, and then talk about the landscape of metal 3D printing technologies that have been used in the past for injection mold tooling. We're going to go a lot deeper onto the technology from my company and what we call our true shape technology and the tool steels that we've developed. And then we'll talk about how molders, tool makers, and OEMs are using the technology to reduce lead times, reduce costs, and accelerate the launch of their products. And as Michael said, please feel free to ask questions throughout this. At the end, we'll be able to answer those questions. So a bit about Mantle. So Mantle is a technology development company. We've developed a metal 3D printer, we've developed software, and we've developed tool steel materials that we sell to molders and OEMs and tool makers to really automate the toolmaking process and reduce the time and cost associated with what is today a very lengthy and time-consuming process. And we're able to do that by producing tool steel components that meet the accuracy requirements and surface finish requirements and material property requirements of many types of tooling. And so we'll go into a lot more detail on that. But before we do that, let's talk a little bit about the landscape and how Mantle fits into the landscape of metal 3D printing, because we're not the first company that's developed a metal 3D printing technology. And we're not even the first company that's been used for tooling, including injection mold tooling, which is the primary application that our technology has been used for. But we are doing it in a different way, and we'll talk about that. But first, let's talk a little bit about just the challenges associated with tool making and why 3D printing can be relevant for it. And I think, as probably most of you are aware, the process of making a tool, making an injection mold tool or extrusion die or a tool like that, is a very time-consuming process. It can take weeks to months. It's very expensive. It can take a lot of very skilled labor, which is hard to find, increasingly hard to find, and increasingly hard to develop. And then, as we've all experienced over the last several years, challenges associated with supply chains and tariffs have made it even more challenging to develop tooling overseas and then import it here, which is a common practice, but one that has been a bit more risky lately. And the requirements to make an injection mold tool, for example, are really amazing. An injection mold tool is an amazing feat of engineering and manufacturing in terms of the accuracy, the surface finish, the ability to produce millions of parts consistently over time. Really an amazing feat to create an injection mold tool. But in order to do it, it takes a lot of steps and a lot of resources. Typically, this is representative here, but you're dealing with not only a quoting process, but sourcing raw materials, creating the rough part, and then a variety of steps in order to create the precision finish that's required for, say, for example, an injection mold tool. It's typically multiple machining operations, multiple EDM operations. Each of those operations requires machine time, requires programming, it requires handoffs, it requires scheduling, and all of that is what contributes to the long lead time associated with tooling and the high costs associated with that. So there's an opportunity, if there's an opportunity to automate this, if there's an opportunity to eliminate some of these steps, that can be of great value. Now, as I mentioned, Mantle is not the first metal 3D printing technology or 3D printing technology on the market. There's a whole host of technologies out there. This slide here shows over 15 categories of printing technologies, hundreds of different companies that are in this market and have pursued this market. But I'm really going to focus on 4 of them that are relevant for tooling or have been used in some cases for tooling. And the first of these is powder bed fusion, or sometimes referred to as direct metal laser sintering. This is perhaps the most commonly used for injection mold tooling. It's essentially a bed of loose metal powders that a laser beam then goes over and etches or welds together those loose metal powders. Then the powder is reapplied, the bed lowers, and that continues on and on again until layers are built up and a 3-dimensional tool is formed. It's a great technology, and it's been used very successfully for types of tooling like custom rubber molds during the prototyping phase, and also for injection mold tooling, specifically when things like conformal cooling have been relevant, when there's a desire to create very unique geometries that can be 3D printed, but that can't be made conventionally very easily or at all. Similarly for things like venting and creating porous structures to improve venting in a molding process. So all those are great applications associated with this technology. There's also the opportunity to build on top of existing tools, to take an existing tool and repair or build on top of it. It's a great advantage of this technology. Unfortunately, some of the disadvantages are that the parts themselves that come out of the DMLS process are fairly rough and generally do not meet the precision standards of tooling. And therefore, a lot of post-processing is required in order to meet those requirements. Similarly, the parts themselves have residual stress built into them because of the laser process, the essentially welding process. And so secondary operations like machining or EDM cause the steel to warp or bend or move, and that makes it more challenging to do those operations. Also, you're dealing with loose metal powders. Not every shop is set up to deal with that. Now, kind of an advancement on that technology is to turn that into a hybrid process that includes not just that direct metal laser sintering, but also machining in order to clean up the surfaces, in order to improve the surface finish and accuracy. And that can be done on top of the powder bed fusion or on top of another technology that's very similar, where you're extruding a bead of powder or wire that's melted onto a build plate. In this case, again, this is a hybrid process. You're machining, and you can build on top of an existing tool to get very good accuracy. You're able to get the design freedom that comes from 3D printing. But again, the challenges are you have a part that has a lot of residual stress in it. The tool itself has a lot of residual stress, and it can be very challenging to do those secondary operations because of warping and bending. Also, these systems tend to be very, very expensive and really haven't been adopted very widely as a result of that. A third category is a material extrusion process, often called a MIM extrusion, where essentially you have some form of media, a filament or a rod that's made of a metal powder, and it has some form of a binder and a wax that encapsulates it. And then that is 3D printed, it's extruded. And then later there's a debinding step and a sintering step in order to turn that into metal. And this has been used very successfully for things like jigs and fixtures and different types of tooling that generally don't have the same level of precision or accuracy requirements that, say, injection mold tooling has. But it's been very successfully used for lots of different types of applications. It's also generally a low-cost solution, low maintenance, easy to use. But in general, the parts themselves are fairly rough, and they don't, again, meet the surface finish requirements, the accuracy requirements of tooling, and a lot of post-processing is required. Similarly, the parts themselves are not very dense, and you're not able to create parts that have you're not able to create kind of thick cross sections, and you get a lot of shrink, and you're not able to control the accuracy very well. And finally, there's binder jetting. Binder jetting is a process where you have a bed of metal powder, and then a binder is applied on top of it. Then there's a curing step that cross-links that binder before it's then depowdered, and the parts are placed into a sintering furnace. And it's used to create all sorts of great end-use components, including some images here. And that's really more the target for this type of technology, is for end-use components, which it can make, in many cases, at relatively low costs and high volumes, because many parts can be made at once. Now, again, you have the challenges associated with thick cross-sections, and also the challenges associated with a high shrink rate that make it very difficult to control the accuracy. So if I were to summarize all this, for the most part, these technologies are capable of producing a rough part, but still there's extensive post-processing or secondary operations that are required in order to meet the standards associated with tooling. So you still have a lot of these same EDM operations and other operations in order to meet the requirements, which drive up the time, drive up the cost. And as a result, these technologies have generally not been adopted widely for tooling. But we'd be very interested in understanding a little bit more about your experience here. So there's this polling question here that'll pop up. We'd love your feedback on what your experience is. Do you have a metal 3D printer that you use for tooling, or have you used plastic 3D printers for tooling in some cases for low volumes, or have you outsourced this, or perhaps no experience at all? We'd love to hear a little bit more about your background. So that's should be on the screen, and you can answer it throughout the session here today. Now let's shift our attention, though, and talk a little bit more about Mantle. So as I mentioned, we've developed our technology specifically for the needs of the toolmaking process. And as a company, we've been doing this for 7 years. So we've been developing the technology for 7 years. For the first 5 of those years, we worked fairly quietly. We really didn't tell anybody what we were doing. And we worked with a couple of tool makers and molders and OEMs to give us some feedback and to make sure that we were meeting the requirements of the industry. And we understood those requirements to be what's shown on the screen here. And what we've developed is a technology that produces tooling components that have surface finish that's comparable to what you get from, say, a sinker EDM process, or 1 to 3 micron RA. We hold tight tolerances and accuracies of generally plus or minus a thou per inch. And then the ability to hold very sharp features and crisp edges and the types of features that are often used in injection mold tooling and extrusion dies and other kinds of tooling. Like other 3D printing, we're able to take advantage of the flexibility that comes from a 3D printing process and do things like conformal cooling designs for improved cycle times and optimized thermal management. And we're able to build those geometries right into the part as it's being printed, and there's no extra kind of cost associated with that. We've developed tool steel materials that I'll talk more about, but we have an H13 tool steel and we have a P20 tool steel that we call PBEX, and we're developing other tool steels like a 420 stainless. And we've tried to develop this system so that it's very easy to use and can be dropped right into a tool room, right into a shop, and that it doesn't require a lot of training and expertise and programming in order to operate our system. So this is what we've been developing. We've deployed this now with beta systems last year, and we're deploying now this year our first production systems and expanding the deployment across North America. So the technology of what we've developed really consists of 3 main things. There's tool steel materials, there's software. It's very much a software-driven, software-controlled process. And then machines, equipment. The machinery includes 2 different pieces of equipment that I'll explain, including a printer and a sintering furnace. The printer is shown in the far right image, the printer's on the left, the sintering furnace is on the right. So the tool steels, how do the tool steels work? Well, what's unique about Mantle's process, and one of the unique aspects of our technology, is that our tool steels start their lives as pastes, metal pastes. You can think of it like a toothpaste or a thick paint in terms of its consistency. And essentially what it is a combination of metal powders, metal particles, a little bit of binder or glue to hold everything together, and some solvents that allow the material to flow together. And this slurry is what we print. So we print this paste, we deposit the paste, and we extrude it in a manner that's similar to many other types of 3D printing, where you extrude a material and build something up layer by layer. We extrude this paste, and then as we print, as we extrude, after each layer, we heat and we dry the paste, and that removes the liquid. And so you're left with the metal powders, the metal particles, and a little bit of glue or binder that holds everything together. And at this point, it has the consistency of, let's say, a dense foam or a crayon. So it's no longer in the liquid state. It's stable enough to hold the shape of what's been printed. And it's also in this state that we introduce the next operation, which is a machining operation or a shape refinement operation. So our process is also a hybrid process, meaning we incorporate both 3D printing and machining in order to clean up the artifacts of the printing process. So by machining, we're able to clean up the edges, we're able to remove any artifacts of the layer building that takes place from the extrusion process, and we're able to then produce a component that meets the accuracy and surface finish requirements of many forms of tooling. In this process, we'll repeat, meaning we deposit the paste, we heat and we dry it, we machine, and we do that iteratively as we build up a tooling component before finally then taking that tooling component that's been built and transferring it from our printer into a sintering furnace. And inside the sintering furnace, we elevate the temperature to just below the melting point of the steel, so it's a little less than 1400 degrees Celsius. In that process, the metal particles all fuse together. That trace amount of binder or glue is removed. And as the part cools off, as the tool cools off, it turns into dense steel and takes on the properties of, for example, H13. So our H13 steel is chemically equivalent to any other H13 steel. The only difference is it starts its life as a paste, which allows us to print it and shape refine it when it's in a very soft state. And then when it turns into steel, it's durable tool steel, just like any other H13 steel. Now, as I mentioned, it's very much a software-driven, software-controlled process. No programming is required. So the software that the user interacts with creates all of the tool paths. It creates all the tool paths for printing, and it creates all the tool paths for machining. And so the operator doesn't need the skill associated with CAM programming or machining. Instead, they can just upload the model, and like many other types of 3D printers, we generate all of the instructions, all the G code that's then sent to the printer and run. So we'll show a little video here that illustrates this process. And I'm going to highlight here on the picture on the left, which is a picture of our printer. The printer looks like a CNC machine, and that's because it's built upon a CNC machine. So we take advantage of it's a RoboDrill style CNC machine with a FANUC controller and all the capabilities that come from that very tested type of technology. We build on top of that and use the multi-axis positioning. We use the tool changing capabilities, all the control capabilities in order to control and run our printing process. And we add to it the things that are necessary for printing our material and for handling the material during the printing process. Let's see here. So here comes a brief video that's going to show this process on one of our printers. And so it starts in the software, and what you're seeing here is an operator calling up a build that had been uploaded into the system based on the CAD file. So it starts with your CAD file, your tool design, just like any other tool design. As I mentioned, we generate all the G code or all the tool paths and send that to the printer. The operator then loads up the paste, which comes in those 1 liter tubes, loads up what you're seeing here, a build plate, and then the printing process starts. So we extrude the material, we're printing here, and we build up layer by layer. But after each layer, we heat and we dry, and that removes the liquid. And so we're removing the liquid and converting what was a paste into something that's like a foam that can be machined very easily. And the machining generally takes place in a couple operations. One is after every layer, we'll do a very quick facing operation to remove a small amount of material and make it perfectly flat before the next layer. And then every 10 layers, we do this shape refinement that you're seeing here, where we clean up the edges. We're not cutting the features. Those have been printed, but we're just cleaning them up in order to improve the accuracy and the surface finish. And it's iterative, meaning the process just repeats itself. The heating and the printing, the heating, and the machining, that process repeats itself before we then transfer into the furnace. The sintering furnace run will last anywhere between 30 to 42 hours, depending on the size of what's being sintered. And then when it comes out, it has the tool steel properties of what we discussed with respect to our H13 and our P20. And you're seeing right here the finished quality or output of right out of the furnace. Okay. So I mentioned that we sit on top of a CNC machine and we take advantage of the tool changing capabilities of the CNC machine. And we have a range of cutters that we use. The smallest cutter that we use is a 6-thou ball cutter. I'm going to show here a picture. You're seeing the picture on the screen, but I'm also holding up to the camera the same component. So the 6-thou ball cutter leaves a 3-thou radius. So again, that's very much like an EDM process, but all of that is achieved without any programming in a very hands-off way. And so again, we use a range of tools. That's the smallest tool that we use, but we cut different aspects depending on what is required with different types of tools. So the tool steels, what really matters here is that the tool steels have the properties able to withstand the rigors of an injection molding process or an extrusion process. We've developed two steels already. The first was a P20 steel, which has a hardness of about 32 to 34 Rockwell. Then we also have developed an H13 tool steel, which has a Rockwell of 42 on the C scale and can be heat treated up to the low 50s as a secondary operation. Really, H13, I would say, is the workhorse right now. That's what most folks are using. And we have a new material that's in development and testing right now with partners, which is a 420 stainless steel that we're going to continue to develop this year and release later. So that will continue to expand the breadth of the steels that Mantle will offer. One of the key things that we've tried to emphasize with our tool steel development is that our tool steels behave just like any other tool steel in terms of the secondary operations that you may want or need to perform on them. So whether that's machining, drilling, grinding, tapping, EDM, I'm holding up here what you see pictured on the left. This is originally started as a printed block, and then all these operations were performed on it. And what's important is that those operations didn't need to be changed in order to perform them on Mantle steel. So the same operations, same types of settings allowed for the results, and the steel itself is stable and remains flat. So after all this material, for example, started as a big block and all the material was removed, it held within 7/10 flat. Similarly, texturing, polishing, all that can be done on our steel. It's been polished up to an A2 level. And then operations like welding can be performed, and we've demonstrated with partners that they can be done. And there's, again, no difference in terms of how they're performed, and that it can be done in such a way that there's no halo effect or any remnants associated with the welding process. So the goal is to be able to fit right into the tool-making processes that companies have today, but do so in a way that's simpler, that's unattended, and that reduces the time and cost associated with making these tools. So that's a bit of overview of the technology itself. Next, I'm going to talk about how some of our customers, how molders, how tool makers, and OEMs are taking advantage of the technology, incorporating it into their processes. I'm going to start with Nicolet Plastics. So Nicolet Plastics is an injection molder out of Wisconsin with multiple operations. They have their own tool making team, and they do tool making internally, as well as working with suppliers who provide tools to them. But part of their strategy is they wanted to be able to offer more complex tools to their customers in a shorter period, and ultimately deliver plastic parts in a shorter period of time, so that they can accelerate the launches of their customers and get engaged earlier in the development process with their customers. So one of their customers is Gamber Johnson. Gamber Johnson makes a variety of components that are used to connect things like tablets and computers and phones to emergency vehicles. And so there's a wide range of vehicles, a wide range of tablets that need different types and sizes and shapes of these attachment devices. And it's changing all the time. So it's a kind of high mix type of environment. And the components that were needed in this case, it's a latch, needs to be molded out of a challenging plastic, a 35% glass filled plastic. And it has a lot of very complex features that would typically have required a lot of EDM and a lot of different types of operations in order to produce the tool needed to mold this. So it would be a time consuming and expensive process in order to make the tools for this generally. Nicolet said that it would typically be about 180 hours of toolmaker time in order to create the 3 tooling components that are needed to mold this one latch part. And it would have taken them about 6 weeks to go from part design and tool design to the tooling process, and ultimately to the molded part that they could ship to their customers. And in the case of this example, Mantle printed these components, these 3 tooling components, and then Nicolet Plastics finished these components, and it required about 10 hours worth of finishing in order to do things like clean up around the perimeter. I'm holding up one of the components here. So clean up around the perimeter. We printed starter holes for the ejector pins, and they wired those out in order to meet the accuracy requirement of the tenths needed for ejector pin holes. So doing that type of work took about 10 hours. Took about an hour, hour and a half of time on the printer itself and transferring between the printer and the furnace and working in software. So all told, it took about 11 and a half hours of toolmaker time. The printing itself took 150 hours. That happens completely unattended and it can be over a weekend and that type of thing. But the total toolmaker time went from 180 hours down to 11 and a half hours. And the time to launch and mold the plastic part went from 6 weeks down to 2 weeks. So you're able to get the molded part in the hands of their customers that much more quickly. So that was the value for them, and doing so in a way that was unattended and that didn't tax their tool makers as much. They have a, like most folks, they have a relatively small tool making team, and they're incredibly busy and taxed. And so the ability to increase the throughput through the tool room was of great value to them. So another example is with Fathom and their Summit Tooling Group in McHenry, Illinois. So in this case, it's similar in that Fathom needed to mold a very challenging material. It's an overmold of a 60% glass-filled nylon, needed to use a steel tool for it. And in this particular case, though, the tooling requirements that they had were actually a little bit beyond the requirements of what Mantle could print. So I'm showing a close-up view here. There's some features here that were thinner than what Mantle can print. Typically, we can print about 1 millimeter wall thickness. But you can see some of these ribs are less than that, and there's some features that are less than that. And so what was important to them is that they could still do the EDM operations on the Mantle printed component and do the polishing operations and have all that be seamless. And so they were able to do that, whereas when Mantle printed the tooling components, Fathom did the final finishing work. And they still had to do EDM, but it took what would have been 100 hours of EDM down to 27 hours of EDM, and total toolmaker time from 200 hours down to 110 hours. So they're able to really reduce the amount of time from their toolmakers and get that plastic part in the hands of their customers more quickly. Now, a key question that a lot of folks have is the durability of our steel. So Mantle's tool steel, as I mentioned earlier, our H13 is chemically equivalent to any other H13 out there. It just starts as a paste. That's the only thing that's different about it. But Tessy Plastics, a large molder out of upstate New York, wanted to evaluate the durability of our steel. And so they have an existing tool. It's a 32 cavity tool that makes these plastic components that are the thumb wheel screw for a deodorant package. Produce millions of these every year out of a 32 cavity tool. And so what they did is they replaced 2 of those inserts with Mantle printed inserts. I'm holding up one of them here as an example. These inserts, we printed one in our H13 steel, one in our P20 steel. And Tessy did a minor amount of finishing, didn't touch any of the part detail, just did a little finishing around the sides in order to drop it into their mold base. And then put it in the mold base. This is over 1.5 years ago, and have been running ever since. And so this is now over 1.65 million cycles and counting, with no signs of wear on the printed tool. Now it's molding a polypropylene type of material, so not as challenging from a plastic perspective as some of the other examples, but there are S7 slides that cut across the top here. And after all these cycles, no sign of wear or galling. And this continues in production, and these parts are production parts that are making it out to their customers. So it's a testament to the durability of Mantle's tool steels. Another example of a customer is Westtech Plastics. They're a molder here in Livermore, California, that has in-house tool making capabilities. But for the most part, their tool making capabilities are centered around tool maintenance, tool repair. But they would like to be able to offer more tool making to their customers, and again, compress the time it takes to get a molded part in their hands of their customers. And the situation they had is they were in the process of building a very large multi-cavity tool for a medical device customer, but there was a design change. And the customer wanted to validate that design change before proceeding ahead with this large multi-cavity tool. And so very quickly, Westtech was able to design the tool and print it using Mantle Technology, perform a minor amount of finishing work as they dropped it into a mold frame, and then molded samples that they were able to, TPE samples that they were able to then share with the customer, validate the design, and then proceed with the larger program. There was a 50% cost savings here, and took active operations time, toolmaker time, down from what would have been 40 hours to 10 hours. And this is again using our H13 tool steel. Another example is with Westminster Tool, a tool maker out of Connecticut that is a Mantle customer and has one of our beta system last year. Their customer is Pepsi, and what Pepsi wanted to do was test out in a tool steel a new type of design for the bottom of a plastic bottle. So you might recognize the bottom indentations here of a plastic Pepsi bottle. And Pepsi wants to iterate on all sorts of designs and test out all sorts of different designs and optimize the molding processes, the blow molding processes for making these plastic bottles. They wanted to use conformal cooling in order to optimize the thermal properties and improve the molded part quality, the blow molded part quality during their prototyping phase, during their product development phase. And then it wanted to very quickly test out different sizes, different iterations of the bottom sections here. So they used a conformal cooling design to remove the heat during the molding process and to lengthen the life of the tool. This was an example of a very quick project where Westminster was able to work with Pepsi on the design and go from the design to completing the print and doing the minor finishing work, which included kind of grinding the top and bottom, and then getting into the blow molding setup that Pepsi has, all within 9 days. So they're able to get molded parts out much more quickly than they would have been able to otherwise, while taking advantage of unique geometries. Another customer of Mantles is a very large medical device OEM that's used our technology for a number of different applications, including one shown here. And the initial goal of this organization is really to reduce the time it takes to launch products, to get products out to market more quickly. And by doing tool making and molding in a more efficient manner in order to be able to do so, using production representative plastics and production representative tools. Using a steel tool is really important during a medical device validation process. And so the ability to quickly produce a steel tool and steel tool components and mold parts quickly is of great importance during a product development process and ultimately to launch products. In this particular example, it's to mold the component that you could see on top there, a screw mechanism. It requires these 4 nose pieces that you see in the lower left, or excuse me, lower right, that come together to form that screw. In this particular case, Mantle printed the tops of those nose pieces, and then they were assembled into a mold frame in the bottom sections of that mold frame there that you see labeled A, B, C, and D. And the total time, they had good benchmark data on this, it took the total time, what would have been 12 weeks, down to 4 weeks in order to go from, in order to create this entire tool, including the mold base, and begin molding the parts, and to reduce the cost of the tooling from a little over $60,000 to a little over $20,000. These tools were all accurate within 1 thou as printed without any additional finishing. And that's typical. Generally, we hold plus or minus 1 thou per inch. So those are some examples of what our customers, OEMs, molders, tool makers, are doing with our technology, and a little bit more about how our technology fits into the landscape of other metal printing technologies and other technologies used to make tooling. So that's what we prepared. I see there are a lot of questions, so we'll start answering these questions here, and we'll go from there. So I'll, yeah.
Thanks, Paul. But before we get to the Q&A, I want to ask everyone to direct their attention to the webinar survey available on the right of the presentation window. If you close the survey, you can reopen the widget by clicking the icon along the bottom of the screen. And thanks in advance for filling out the feedback form. It makes our events better for you. And now onto the Q&A portion of our event. As a reminder, to participate in Q&A, just type your question into the text box located to the right of the presentation window, or click the Q&A icon at the bottom of your screen. If we're not able to get to all of the questions submitted, we will be sure to give them to Paul to answer offline. So Paul, let's get right to it. You're right, there are a ton of questions in there. Let's start out with a question from Ram, who says, it looks like your process incorporates powdered metal technology as opposed to wrought steel. That being the case, is it considered to have 100% metal density?
Yeah, great question. And the answer to that is no, we are not 100% dense. The output of our process post-sintering is roughly 97% dense. We would not therefore recommend that you use our technology to make, say, a component for an aircraft engine. That typically requires a higher level of density. But in all of the testing that we've done and all the feedback that we've done, it is more than adequate for tooling, for including very high volume tooling, like the example I gave with Tessy Plastics that is in the millions of shots. So that is just a reality of our process, a consequence of our process. I will also note that it's possible to actually make our steel less dense. So in some cases, it's advantageous to have less dense steel and allow for airflow for venting purposes. And that's a possibility with our technology as well. We found that we could sinter the only difference is we sinter a little bit differently. We found that about 85% dense allows for really good airflow while still molding successfully the plastic part. So that's something that is a little bit more, I would say, in the development mode. It's not been kind of adopted widely, but is a possibility with our technology and something that can be an advantage for certain types of molding processes.
Terrific. Keep the questions coming. This one from Richard, who asks, how long is the centering process versus printing time?
Sure. Yeah, great question. So the printing time is variable. Printing time depends on a variety of factors, including the size of the part. I would say the biggest impact is actually the Z height, the height or the tallness of the part. A taller part will take longer to print. And so that's printing, and I'll come back to that. Sintering is almost always the same, or the same range. So sintering is anywhere from 30 hours to 42 hours, depending on the size of what you're sintering. Something that's larger might be up to 42 hours. And you can sinter multiple things at once. In fact, one sintering furnace can support multiple printers, which is a common scenario. So that can be more of a batch process and happens in that way. But printing is variable depending on the size of what you're printing. The time scale is typically days. Something that's relatively small, like this, you could print in less than a day. But if you're starting to talk about something with a lot of feature detail, it's going to take a little bit more time to machine, and also that's got some height to it, then you're talking on the order of days. So an example with this particular project with Nicolet Plastics, there were 3 components that were very similar in the size, or I should say 2 components that were similar to this size, and then one smaller component that we could print all at once, but that was about 150 hours. Now that's a little bit on the longer side, but that was 3 components at once. So a time scale there, though, is you could produce, say, a cavity core section for a modest size insert, let's say 4 inches or less. You're printing that in roughly 2-3 days, 2 to 4 days, depending on the complexity. And then sintering, so within a calendar week or a work week, you're getting something that is then ready to be finished. So that finishing work can take place within a day or a couple of days, and you're molding parts within a couple of weeks. Is the typical time scale out of a steel tool.
Great, thanks for that. Keep the questions coming. We've got a ton in the queue. Mark wants to know, what is the shrink post-sintering?
Yeah, so definitely the shrink does occur during the sintering process. There's no doubt about that. But our rate of shrink is considerably less than the shrink rate associated with other sintering-based technologies. So our rate of shrink is less than 9%. That compares to 17, 20, 25% that's associated with other sintering-based processes. And we've invested a lot of time, a lot of development time in order to minimize that shrink and make that as low as possible. And the reason why that's important is because that allows us to hit the accuracy and the tolerance requirements of tooling much more effectively. If you're shrinking a lot, it's a lot harder to hit the tolerances. So by shrinking that small amount, we're able to hit the tolerances better. And it's consistent and it's predictable. So we know the rate of shrink before printing, and we gross up the part. So we print the part a little bit bigger, and then to accommodate the shrink so that it comes out of our process consistent with the CAD. And all of that is managed in our software. So the user doesn't need to kind of do that math. Our software accommodates for that and makes the part bigger.
And again, let me remind you, keep the questions coming. We will get to as many of them as we can in the time we have left. The ones we don't have time for will be delivered to Paul afterward. Mike wants to know, what's the size limitation for this process?
Yeah, great question. So the build envelope for our printer is 8 inches by 8 inches by 6 inches. That's the maximum build envelope for this generation of hardware. We recommend for a single insert to be within, say, 5.5 inches by 5.5 inches by 2.5 inches. That's what our design guidelines recommend as an optimized size and smaller for a single component. We continue to make that larger over time as we optimize our printing process, but it won't get any bigger than that 8 by 8 by 6 with this generation of hardware.
Okay, terrific. Thanks for that. Richard wants to know, what's the accuracy you can get?
Yeah, so accuracy is plus or minus 1 thou per inch. So for a component that's 1 inch, we'd say we'd be within 1 thou. If for a component that's 4 inches, we'd say we would be within 4 thou.
Okay, thanks so much for that. Luis says, what's the tightest tolerance for tolerances such as a true position and profiles?
The tightest tolerance, again, that would be the accuracy of plus or minus 1 thou.
Okay,
1 thou per inch.
Great.
Yeah.
Ram says powdered metal may not yield equivalent toughness to withstand impact resistance compared to solid metal. Am I right?
What we've found is that the impact resistance, again, for what we have, which is 97% dense, is suitable for tooling and has met all the needs of tooling, including at very high volumes. There may be applications that have requirements beyond what our steel could achieve, but for tooling, we found it to be more than adequate.
Daniel wants to know, do you have customers that make gauges and text fixtures?
Certainly that's possible. Yeah, you could. So really any type of metal component where you need some precision can be produced with Mantle. Now there are some design constraints and limitations. For example, we cannot print an overhang that's over 45 degrees. So we can print something that's like a ledge underneath that. So if you had a feature that required that, then we wouldn't be able to print it. We'd have to print it solid, and then you'd have to machine it out separately. So if that's acceptable, then you could certainly use it for gauges, for fixtures, for all sorts of different things. You're not restricted in using it for tooling. It's just we've made the decision as a company to focus our efforts, our development efforts, our commercial efforts on the toolmaking market and developing our needs to meet developing our technology to meet needs of the market.
Yen wants to know whether it's possible to use both additive, like 3D DLMS, and subtractive, like machining, together to achieve a faster turnaround, and if so, how do you do that?
Yeah. Well, in some ways we already do. So as I mentioned earlier, and I described our process is a hybrid process that includes both printing and machining. Now we're machining something though that's not in the steel state. We're machining something that's still in the kind of printed state. And so it's very easy for us to machine. We can machine very quickly. But once it comes out of our sintering furnace, then you certainly can do machining operations. Here's an example of something that's had a lot of machining done to it in order to improve the accuracy or do EDM or a variety of things that might need to be done. So that's very much possible. Now, what's not possible with Mantle's process, but is possible with the DMLS process that I described before, is to build on top of an existing tool. So if you have an existing tool and you want to build on top of it, that can be done in some of these DMLS processes, including the hybrid DMLS processes. Those processes tend to be really, really expensive. So that's not been done a lot, but it is possible to do.
Keep the questions coming. Kyle wants to know, what's the secret sauce? He says, what are the key improvements or advantages to Mantle as opposed to competitors?
Yeah, the secret sauce. Okay, well, I would say from an output perspective, in terms of what comes out of our process, the key thing that's different from other metal 3D printing technologies is the level of precision. It's the level of accuracy. There's no other metal printing process that has the surface finish that we have in terms of 1 to 3 microns RA, or what you'd get from a sink or EDM. There's no other metal printing process that can achieve the tolerances that we achieve. And there's also no other printing process that's been designed specifically for tooling and to drop into a tool room. So I mentioned our 3D printer is built on top of a CNC machine. That means it needs only standard shop air and standard shop power and can sit alongside your other CNC machines. Our furnace, similar. It's a standard vacuum furnace. It can drop right into a tool room. So we've designed our system to be able to drop right in, and we've also priced our system. I didn't talk about this, but our system cost is only $230,000 for our printer and $120,000 for the furnace. So a set, and to get started, it's $350,000. But as I mentioned, one furnace can support multiple printers. And by comparison, many of the other 3D printing technologies are considerably more than what I described, and really have been out of reach for most tool rooms, and required a lot of facility modifications in order to kind of accommodate them. So it really hasn't been adopted very widely. Our goal, and what we're already doing, is being able to drop right into a tool room, have a price point that's comparable to what folks are spending today on capital equipment inside their tool rooms, and it can be adopted very easily.
Here's an interesting comment from Ram. He says, from what you've outlined, there's an opportunity to not only improve operational efficiency, but also improve overall energy efficiency, in which case a project might qualify for a utility-sponsored energy efficient incentive programs to help the funding of a given project.
Yeah, absolutely. I mean, there's certainly some advantages to additive in the sense that you're not starting with a big block of steel and machining all sorts of things away, which leads to waste and takes energy. So there's certainly some advantages there. And we'd be happy to partner with you and or anybody else to kind of explore that further and pursue some of those grants.
Yeah, let's call PG&E right now. Come on.
Yeah.
So James says he's a toy maker. Do you create tools in-house, or do you refer to your tooling customers?
Yeah, great question. So Mantle's business is not to be a tool maker or to make tooling components and supply them to folks. We want our customers to do that, and we don't want to compete with our customers. So our customers include tool makers, they include molders who offer both molding and tool making capabilities. And yeah, our strategy is to then point people who maybe are not interested in having Mantle equipment in-house. We would point those folks to our customers who could have tooling components made. We do print things for people who are interested in evaluating the technology. So if people want to do a test before they invest in our technology, then we print things for people like that.
Thanks again. Keep the questions coming. We've got just a few minutes left before we need to wrap. Rick wants to know if you're aware of companies that already have a Mantle system and offered sintered tooling components ready for final machining.
Yeah, absolutely. So again, it's kind of part of our strategy is to have our customers do that work and build businesses around that. And so our beta customers that we deployed last year, one of them does that as a service, Westminster Tool. So they have our system and they offer that as a service to people. The other is a med device OEM, and they use it just for internal purposes. This year, starting actually later this quarter, we're shipping our first production systems. One of them is going to Nicolet Plastics. Another is going to Westtech Plastics. Both of them intend to offer it as a service to other people. And that would be a great resource to use if you want to have something made. And we can put you in touch with them and broker those discussions if you're interested.
Terrific. So reach out after the event. Kevin says, well, you mentioned the cost of the equipment. Do you make mold components for customers as a service? And what's the typical cost to make a 5x5x2 mold core and cavity?
Yeah, again, we do not make it as a service. So that would be, the cost would have to come from our customers. They have to tell you what the cost they would charge for you for something like that. So that's not something that we offer as a service.
Yeah, Scott wants to know if you're signing up service bureaus.
Yeah, certainly we're engaged with some. Now, we want our customers, though, to not be, I should say, we want our customers to have competence and expertise in tool making and plastics molding, because that's what we've designed the technology for. And we recognize that we produce something like this, but there's some finishing work that would be required to get it into a mold. Typically, you need to maybe grind around the outside. You, of course, need to have the mold base. That's not something that Mantle has. There are all sorts of other components that go into a mold base. So we want our customer base to have that level of expertise to be able to deliver solutions to their customers.
And John asks, what particle size or size range do you typically use?
We use a range of sizes. It's a good question. It's one of the advantages of our technology and of the approach of using a metal paste. We're not restricted to having to use the same metal particle size and shape across the board, which other technologies need to do. So we can use different metal particle sizes and shapes. And one of the reasons why that's valuable is because we can improve the packing density. Basically, we can get those metal particles closer and closer together. And that's important for the shrink rate that I talked about earlier. So I mentioned we've invested a lot of development time in order to reduce that shrink rate to below 9%, which is far better than anybody else in the market. And one of the reasons why we're able to do that is because that we can use these different metal particle sizes and shapes in our paste. And then that improves the density and the quality of the sintered part.
And Michael wants to know if you could remind him of the maximum dimensions of a 3D printed mold.
So the maximum dimensions of our envelope, our build envelope, are 8 inches by 8 inches by 6 inches. Today, we're recommending that folks stay within 5.5 by 5.5 by 2.5 as a single insert, but that is going to continue to expand as we continue our development work.
Terrific.
But you can also, I should note, you can print multiple components at a time that are smaller and all fit inside that 8 by 8 envelope. So you could line up 6 or 8 of these inside of one print and print them all at once. And that leads to efficiencies in terms of print time and individual component cost.
And this one comes from Alice, who says, can I polish, plate, and weld your materials?
Absolutely. So we have done a lot of work there to demonstrate that can be done. We have documentation about that on our website. We have, for example, what we call the H13 material performance study. that includes the results of testing done and work done by third parties, by independent third parties to do things like polish. This is polished to an A2 level. This was laser welded by PLT, precision laser technology. You've got texturing and etching and all sorts of different things on this. And what's important there is not only can you do it, but you can do it in a way that is no different than doing it for any other tool steel. And so you don't have to change your operations in the way that you do that.
We have time for just a couple more questions. This one from Scott, who wants to know, what is the steel cost per liter?
Sure. Yeah, so we charge, our metal paste comes in tubes, cartridges, and it's $625 per liter for a tube of H13 paste right now. But what's important, and that's certainly more than a block of steel, the block of H13 steel. If you just go out and buy wrought steel, it's going to be a lot less than the cost of our paste. But what's important, we think what's important is not so much that cost comparison, but the cost comparison of producing a component like this, producing the end component. And our target, and what we've demonstrated time and again, is that the cost of producing that component with Mantle is comparable to or less than cost of producing that component via traditional tool making processes. Not even compared to metal 3D printing. Metal 3D printing, we're simply less than. But compared to traditional tool making processes, our target is to be comparable to or less than that. And that's when you factor in not only the cost of the material, but the machine rate of our system compared to the machines of all the other systems that are needed traditionally, compared to labor, which is really low with our system, but high with making it conventionally, consumables like electricity and power. When you add all that up, the total cost, our target is to be comparable to or less than, and a lot faster than what it takes to make it traditionally. And we're doing that in a way it's a lot simpler as well, because it doesn't require a lot of handoffs or a lot of people. And so again, we've proven that time and again, and we're happy to do that analysis and evaluation for your specific geometries.
So I want to know how clear your crystal ball is, because Michael wants you to make a prediction as to how far we are away from seeing 3D printed tool that's, say, 30 by 30 by 30.
Well, it's probably not impossible. There are certainly technologies out there that are pushing the envelope, getting larger and larger. It'll be a long time before you see that from Mantle. That would be beyond our even next phase. We're sticking with 8 by 8 by 6 right now, and kind of smaller types of injection mold components and other types of components for things like extrusion and die casting and so forth. But it's possible, yeah, probably. It would probably take a long time to build something that's that big, though. Print time would be
Finally, I think we touched on this already, but this is a question that came in from Margaret, who wants to know, do the parts shrink in the furnace, and if so, how much, and do I need to account for it?
Yeah, so they do shrink. I mentioned they shrink less than 9% in the furnace, but you don't need to account for it. So you do your tool design as you always would, and then our software accounts for that shrink, meaning that we print the part a little bit bigger so that it shrinks down and hits the net size that you're looking for.
And that's all we have time for today as far as questions go. I want to thank you for your expertise and your time on today's topic, Paul. It was great. Thanks to our sponsor, Mantle, as well as everyone in the audience. We appreciate your attention and your great participation as well. And within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. So feel free to invite your colleagues and peers who may not have been able to listen with us live today. The webinar is copyright 2023 by Informa, and presentation materials are owned by or copyrighted by Informa Markets. The individual speaker is solely responsible for his content and opinions. On behalf of our guest, Paul DeLaura, I'm Michael Krieger. Thanks for your time and have a great day.